All right, now that we found the eigenvalues, let's now find eigenvectors. And in particular, let's find the eigenvectors of the matrix 1, 6, 5, 2 that we discussed. Now, remember, eigenvectors are related to eigenvalues. So technically, you first need to find the eigenvalues. The eigenvalues. Which we found in the previous video. I believe we found lambda equals 7 and lambda is -4. And remember, eigenvectors are related to eigenvalues. So what we'll first find all the eigenvectors related to 7, and then all the eigenvectors related to -4. And once again, let me motivate this. So motivation. So you start with our equation, AV equals lambda V, which remember, we ended up writing as A minus lambda IV equals 0. And it turns out it's this equation that helps us find eigenvectors. Because now that we're given lambda, we just need to solve for V. So kind of our strategy. So for every lambda you found, solve this equation. So A minus lambda I V equals 0. And because the right-hand side is 0, this is sometimes called the null space. Null space, like null in German means 0, so it's the 0 space. And sometimes that's denoted by null of A minus lambda I. Okay, so let's do this. And again, this is one of the things, it looks so weird if you've never seen this, but we'll do it many, many times. So let's do null. In this case, lambda was 7. So A minus 7i. And again, the way you write this, you put your matrix on the left-hand side. So in this case, I think A minus lambda I was 1 minus lambda. So 1 minus 7, and then 6, and then 5, and then 2 minus lambda. So 2 minus 7. Which, by the way, this looks weird, but this is the matrix you had from eigenvalues. And then to write 0 on the right-hand side, you just add a bunch of zeros. So 2 zeros. So we have that. So once again, you subtract lambda from the diagonals and you simplify. So we have minus 6, 6, and then 5 minus 5, 0, 0. And then the idea is to simplify this. So this is what's called in linear algebra a row reduction or row operation, which here just means try to simplify the equation a little bit to get a nicer form. So one thing we can do, so notice we have the 6's on the first row. Let's divide by minus 6. And for the second row, let's divide by 5. Which gives you 1 minus 1, 0, and then 1 minus 1, 0. So again, in case you're not familiar with row operations, there's 3 things you can do. One is divide a row by any non-zero number. Another thing is swap 2 rows. And the last thing is you can add or subtract rows from one another. So in particular, since this second row is equal to the first row, we can just subtract the first row from the other one. That's what this times minus 1 means. And you're left with 1 minus 1, 0, and then 1, and then 0, 0. And that is kind of your goal. You want one of your rows to be all zeros. And that's what's called row reduction. And that will always be the case, by the way. If it's not, it meant you made an algebra mistake. And now let's see what this means in terms of equations. So if our unknown is xy, so if v is xy, this actually tells us that 1 times x minus 1 times y is 0. Minus 1 times y is 0, and therefore x equals y. And so what is our vector? What's your vector? So v was xy. But since x equals y, this is just y. So here we use x equals y. And now notice the y factors out. So you get y times 1, 1. And what is an eigenvector? It's precisely this 1, 1. So eigenvectors, turns out they come in multiples, but generally we just need 1. So hence 1, 1 is an eigenvector for lambda equals 7. And once again, I know this is overwhelming, but we'll do the same process every single time. We'll do a minus lambda I, simplify this, set it equal to 0, use a bunch of row reductions to solve this equation. Now, huge warning. Pretty much the only mistake you can make here. You should never find 0, 0 as your solution. Never find 0, 0. Eigenvectors, by their definition, actually are non-zero. And if you found 0, 0, this means one of two things. Either you made a mistake in your row reduction, like made a mistake somewhere here, or worse, you found the wrong eigenvalue, meaning you would have to start all over again. That's why my suggestion is, when you find eigenvalues, be very careful, because a mistake there could, cost you all the row reduction. Unfortunately, we're not done. We're just halfway done because we found one eigenvector. Now we need to find another one for lambda equals minus 4. So in this case, we need to find the null space of A minus 4i. Which in this case, you subtract minus 4 from the diagonals. So I think 1, 6, 5, and 2. And you do 1 minus 4, and 2 minus 4. And 0, 0. And that becomes, in this case, 5, 6, 0, and then 5, 6, 0. Which are identical rows. So you can, once again, subtract one row from another, and you get 5, 6, 0. Again, once again, good, we found a row of zeros. So what this tells you is, basically, if V is your eigenvector, then what we have is 5 my tablet unsubscribed. So then what we get is 5x plus 6y equals 0. Now, you can repeat the method from above, okay, solving for y in terms of x and then doing the vector. But here's a cool trick. Since we only need to find one eigenvector here for the eigenvalue, it's okay to guess values of x and y that works. So trick, find one value of x and y, and I'll tell you a recipe soon that works. For example, you could have x is minus 6 and y is 5. Right? Because if you do 5 times minus 6 plus 6 times 5, you do get 0. And by the way, you may wonder, what about 6 and minus 5? Also 5. And if you want, in general, if you have ax plus by equals 0, then I believe x is minus b and y equals a works. Because a times minus b plus b times a is 0. So here, what is the answer? So here v, which is xy, is just minus 6 and 5. So minus 6, 5 is an eigenvector. To 4 lambda equals minus. And next time, what we'll see in the next video is how to combine our two answers to get something interesting. But I do want to say just one little remark, because for eigenvectors, you can get nasty fractions, but the good news is it's actually okay to rescale eigenvectors. And what I mean by this is, suppose you found maybe minus 6/5 and 1. It's okay to multiply both sides by 5 to get minus 6/5. Both of them are legit eigenvectors. Although I may ask you in answers to use integers here.